Hello, my name is Allison Harvey, and in this video I'm going to be focusing on how we can algebraically manipulate functions so that when we are evaluating their limit, we don't get indeterminate statements such as 0 over 0, infinity over infinity, things like that. You get the idea. So before we can really dive into any example problems, we need to really talk about the key ideas of algebraic manipulation and why we do it when we're evaluating limits. So like I said before, the main reason that we algebraically manipulate functions when we are evaluating their limit is when we get statements such as 0 over 0, we really want to avoid that. We want to avoid an indeterminate statement. So we algebraically manipulate. How do we do that though? How do we algebraically manipulate a function so that we avoid these indeterminate statements when we're evaluating their limits? Well, one way is to divide out a common term. This means, such as with polynomials, we factor them down, and if we can cancel out common terms, we do so. We can also multiply roots by their conjugates. So if I have a square root of x plus 2 in my denominator, then I'm going to multiply by the square root of x minus 2 to both top and bottom. We can also eliminate complex fractions, and we do so by finding a common term and multiplying through a common denominator term, that is. So the key idea here is that we want to avoid this. We want to avoid that indeterminate statement. So let's look at some examples. Example 1 we're going to walk through really slowly so that we can really get the idea of avoiding that indeterminate statement and finding a solution. So you can't just plug in or you will get the statement 0 over 0 as you did here. When you see this statement 0 over 0, you need to stop and reevaluate and think, can I factor this? Because this is an indeterminate statement, and there could possibly be a term that this limit is approaching. So plugging in 5 in this example, where the limit as x approaches 5 equals x minus, the limit as x approaches 5 of the function x minus 5 divided by x squared minus 25. We can't plug in 5 because 5 minus 5 divided by 5 squared minus 25 gives us the statement of 0 over 0, which is indeterminate as we've already established. So this is what you want to do instead. You want to factor. So I'm going to look at my function, x minus 5 divided by x squared minus 25, and I'm going to recognize that this is a perfect square. This is not a perfect square. This is a difference of squares. So I'm going to break it apart. I'm going to break up x squared minus 25 into x minus 5 times x plus 5. Now, I notice that I have two common terms in my numerator as well as in my denominator. So I am going to put a big slash through them. I'm going to cancel them out. I'm going to cancel out my x minus 5 terms from both my numerator and my denominator. I can do this because I am multiplying. If this were x minus 5 plus x squared, for example, I would not be able to factor. I can only do this because we are multiplying. Not adding or subtracting, but multiplying. So I'm left with the statement, now that I have canceled out these common terms, I am left with 1 over x plus 5. So now I can plug in the number that my limit is approaching, which is 5. So the limit as x approaches 5 of 1 over 5 plus 5 equals 1 over 10. So we avoided that indeterminate statement, and turns out that there's a value that this function is approaching at this given limit. Okay, let's look at examples 2 and 3. Example 2 is going to deal with multiplying a square root by its conjugate, or any root by its conjugate. And example 3 is going to focus on complex fractions. So example 2, I have the limit as x approaches 3 of the function x minus 3 divided by the square root of x plus 1 minus 2. Sorry. First thing I'm going to do, no, crying is not an option. It's never an option in calculus, as Ms. Jensen has always taught us. So we're going to multiply by the conjugate. So what does that mean exactly? To multiply by the conjugate means you're just multiplying by, as opposed to x plus 1, the square root of that, minus 2, you're going to multiply by the square root of x plus 1 plus 2. That's going to get rid of your square root term and just kind of simplify things so that we can really avoid that indeterminate term. So after I multiply both top and bottom, that's the key here, multiplying both top and bottom by that conjugate term. After I multiply both top and bottom by the conjugate term, I am left with the limit as x approaches 3 of x minus 3 times the conjugate term divided by x plus 1 minus 4. When doing so, this is kind of like the same idea if you can recall back to Algebra 2 and difference of squares. It's kind of that same idea. I'm multiplying by a common term, and then these two are different, so I'm going to be left with, if I were speaking in terms of difference of squares, x squared minus a term, that similar term that is only different in signs. So I'm left with x plus 1, because the square roots have now gone away, minus 4, because that's negative 2 times positive 2 is negative 4. This can be simplified to x minus 3, but we'll get there. Excuse me. So now we are left with the limit as x approaches 3 of x minus 3 times that conjugate term divided by x minus 3. We can now cancel our common term, and we are left with the limit as x approaches 3 of the square root of x plus 1 plus 2. I can now plug in the value that my limit is approaching and solve. So this becomes the limit as x approaches 3 of the square root of 3 plus 1 plus 2, which is the square root of 4 plus 2, which is 4. Okay, now we have example 3. Example 3 states, or it wants us to solve the limit as x approaches 0 of x divided by 1 over negative 1 plus x plus 1. Now with complex fractions, the idea here is that you want to get rid of this often scary denominator term. And how you do that is you multiply by that denominator term so that it will cancel out. If I had multiple terms here, I would be multiplying by my common denominator. So I'm going to do that. So I'm going to multiply my entire function. That's the key with complex fractions. You have to multiply your entire function by that term that you were trying to eliminate. And here that term is negative 1 plus x. So I'm going to multiply my entire function by negative 1 plus x, carrying my limit as I go along. And so I'm going to be left with x times negative 1 plus x divided by the negative 1 plus x cancels out, so I'm left with 1. 1 plus 1 times negative 1 plus x is negative 1 plus x. So carrying on, I'm going to simplify this. 1 minus 1 is 0, plus x is x. I'm going to leave out my x term so that I can factor it out. So I'm left with x times negative 1 plus x divided by x. I'm going to cancel out those x terms, and I am left with the limit as x approaches 0 of negative 1 plus x. I can now plug in my the value that my function is approaching, which is 0. So I'm left with the limit as x approaches 0 of negative 1 plus 0, which equals negative 1.